Welcome back, everyone. I hope that you were able to, grab a refreshment or use the restroom or stretch. So now we're going to be moving on into our next speaker, and that is Jeremy Berry, PhD. He is an assistant professor in the Department of Neurological Sciences at the University of Vermont. Dr. Berry has carved out a unique niche that bridges basic and translational science by employing a systems neuroscience approach to the origins of cognitive deficits that accompany pediatric seizures. His work formalized the temporal coordination theory, which states that a network's ability to dynamically organize cell activity relative to theta oscillations, both within and between relevant neural circuits, is necessary for normal cognition and is frequently disrupted as a long-term consequence of seizures experienced in early life. So I want to give a warm welcome, Jeremy Berry. The floor is yours.
Great, thank you for that, Briandra. So guys, it's a pleasure to be with you all here today, and I thank Dan Abasar, Dr. Abasar, for the invitation. So the title of this little talk I put together is Where We've Been and Where We're Going, the Hippocampus and its underpinning of spatial cognition and memory. So there's a lot of ground to cover today. I'll get into a lot of the history, some technique, and this unique intersection of physiology and psychology. So I've divided the talk into 3 parts. So the first part, how did we get here? A brief history of basic science research into the physiology of learning and memory. Then I'll get into the neurophysiological underpinnings of spatial memory and cognition, and we'll talk about some of these spatially tuned cells and the theory of the cognitive map, and how this gave us a better framework for understanding memory. And the last part, where the rubber meets the road. How does animal work translate to human memory? So here's a list of words. Just as a primer to start out, these words should bring up thoughts of psychological jargon that you've likely heard before. There's habit, attention, consciousness, stream of thought, discrimination and comparison, and my personal favorite, memory and perception of time. So it might surprise you that these words all have one thing in common. They were all chapter titles of a book written in 1890 by the father of psychology, William James. Now, this is just to give you a perspective on how long we've been thinking about these different faculties that we often take for granted, particularly memory, the physiology of which we've only begun to get a handle on in the last 60 years. So every good story has a beginning, and the one that I'm about to get into began back in 1957, when Brandon Milner at McGill University began psychological experiments with Henry Malazan, or patient HM, who, as Willie went a great deal telling me about, had received a bilateral hippocampectomy in an attempt to cure his severe epilepsy. Now, the unintended side effect, as you heard, of this treatment was that while Henry was able to recall the majority of events before the surgery, he was unable to form new explicit memories. Now, as described by Suzanne Corkin in her book, HM lived in a state of permanent present tense. So this led to decades of animal studies, mostly in rats, that cracked the code of how the hippocampus and its simple trisynaptic architecture between the dentate gyrus CA3 and CA1 was able to do something as complex as make new memories. So here entered one of my personal heroes, Jim Ronk, shown here in a New York Times photo from 2010, where he's quizzing New York City subway commuters about which way is uptown. Now, the reason for this will be obvious in a few slides. So way back in 1973, Jim Ronk was one of the first scientists to use microwire to record hippocampal local field potentials and single unit activity in the brains of freely moving animals. So why was this a heroic act back in 1973? Now, apart from the obvious technical challenges, the reason is that the hippocampus was a black box, an enigma wrapped in a mystery. There was no characterization of cell types, no paradigm that would help one make sense of what you'd find there. So Jim used an approach that most of us would use. He decided to just dive in and describe what he saw, an almost ethological approach. Now, one of the most important things from Ronk's paper was a basic description of the unit types he found in the hippocampus. And there are two of them. Pyramidal cells, which he called complex spiking cells, and interneurons, which he called theta cells. So I'm going to jump out of that paper for a moment to illustrate some of these points from my own data. Here's an example of the average waveform from a simultaneously recorded interneuron in green and a pyramidal cell in red. So the pyramidal cell has a very broad waveform, while the interneuron has a much narrower, shorter duration waveform. While the interneuron pretty much fires continuously, the pyramidal cell tends to fire in bursts called complex spikes, and these are separated by 2 to 4 milliseconds. So why are these definitions of single cell recording important? Okay, so as in vivo electrophysiologists, we don't have the luxury of seeing what's at the tip of our electrodes. We have to make important inferences about unit type from the firing properties and waveform properties of the units that we find. So we now know that these theta cells are, of course, inhibitory interneurons, and that excitation and inhibition is basically a fundamental operating principle across the entire brain. And these are what the excitatory and inhibitory neurons look like in the hippocampus, with the pyramidal cell in green and the bistratified interneuron in blue. And these are the axons of the bistratified interneuron projecting to the apical dendrites and to the basal dendrites. Now, if you stimulate the bistratified interneuron, you cause inhibition of the local pyramidal cell that it's connected to. Now, there are a lot of different types of interneurons, but the main point here is that every compartment of the cell, there's an interneuron that's controlling its inputs and its outputs, either directly at the soma, which is the main body of the cell, as well as where the action potentials come out at the axon. Now, if you take nothing else away from this talk today, it should be this: that a cell is a very simple thing. You know, it makes an action potential or it doesn't, but its timing and when it fires is something that's really important for cognition and sensory processing. So I'm about to show you a little video from my own work where there's a rat performing a spatial task. Now, at the same time, there's an array of electrodes in this hippocampus, and I'm filtering these signals two ways, where I can get the local field potential, or the classic EEG signal that you've heard about, or so I can just look at the individual cells that are making these bigger signals. So here's the EEG, a lot of this 5 to 12 hertz theta oscillation, and these big sharp wave ripples where there's lots of cells firing at a millisecond time scale. And you see the theta oscillations mostly when the animal is moving or exploring space. And those little pops here in the background are actually the filtered action potentials from single cells. And these clusters that you see on the screen are representing the action potentials of these cells. So getting back to Jim's paper, and his, let's just look and see and describe what we see. Style, Jim described both the activity of single cells, as you can see in the top line, as well as the local field potentials on the bottom line, in relation to what the rat was doing behaviorally. You can see in this example that while the rat is walking, this CA3 interneuron fires rhythmically and in register with this 5 to 12 hertz theta oscillation. When the rat slows down and theta goes away, the cell's firing rate goes down drastically. Because of this relationship, this is why he called these interneurons theta cells at the time. And this example is from an interneuron in the dentate gyrus during REM sleep, which was back in the day was called paradoxical sleep. Now this is one of the earliest examples of a phasically driven cell where one can see that the cell spikes prefer to fire at the trough of the local theta oscillation. And this is important as it tells us there's a rhyme and reason to when a cell is active, that it takes specific inputs to make a cell fire. So So there are also some lighthearted moments in this paper that I thought I would drop. So that where you put the rat down and it ran off squealing, or we make a loud sound and the rat would freeze. But on the more serious side, Brunk would often introduce food and water and found that pyramidal cells, these excitatory cells, would become active when the rat approached them and ate or drank. And he categorized these cells as approach consummate cells. He also found that the cells would fire where the food had just been, and he called these cells approach consummate mismatch cells. So even though Ronk was doing the right thing here, was taking exactly the right approach, but the categorization started to get a bit problematic. So you're about to see that Ronk missed something very important here, but this remains a landmark descriptive paper for electrophysiology and was really the beginning of this whole enterprise that started making this distinction or this relationship between the physiology and the activity of cells and behavior and learning and memory. So fast forwarding about 45 years, we now know that the hippocampal and entorhinal cortex help to form a basic spatial coordinate frame for navigation and memory. Okay, so if we take a horizontal cross section through the hippocampus and the entorhinal cortex, we see this beautiful layered architecture with 3 layers in the entorhinal cortex and these interlocking horseshoes, the dentate gyrus, CA3, and CA1, which comprise the hippocampus. And it's for a very simple reason that we talk about circuits in the brain, as everything tends to be connected like a circuit. So layer 2 of the entorhinal cortex projects to the dentate gyrus projects to CA3, and CA3 projects back to CA1. Layer 3 of the entorhinal cortex projects directly to CA1, and this whole circuit is complete when CA1 projects back to the subiculum in layer 5 of the entorhinal cortex. All right, so John O'Keefe in the early 70s beat Ronk to the punch and found that hippocampal pyramidal cells tend to fire in these circumscribed receptive fields, which he called place fields, and I'll get more into that in a little bit. Now, Edvard and May-Britt Moser in the early 2000s found that layer 2 entorhinal cortex cells tended to fire in this repeating equilateral triangle pattern, which they called grid cells. In layer 3 and layer 5, there are also head direction cells. Now, these were first discovered in the early 80s by our hero, Jim Ronk. He likes to say that he was mentally prepared for that one. And these cells don't fire relative to position per se, but are more receptive to which direction the head is pointed in. And this signal is really important for orientation. There are also conjunctive cells, which are both grid cells and head direction cells. And finally, there are boundary cells which fire at sections of walls that the rats can't get through. Now, we're still really trying to piece all this together, and some think of this circuit as kind of a comparator, where the sensory-driven entorhinal cortex tends to process the world as it is, whereas the stored representation of space is in CA3, and these are all compared then in CA1. So if you wanted to do, as an example of how the circle might work, if you go back to your living room after this talk and you find the group in your living room, right? You might be able to use the circle to say, well, this wasn't here before. And this is a very kind of an oversimplified way of looking at it, but it's still the best framework we have. Okay, getting back with the cell that started it all, hippocampal pyramidal cells. So shown here are 4 simultaneously recorded place cells. So together their firing fields cover the whole environment, and as an ensemble are able to signal the rat's location no matter where it is. So as proposed by John O'Keefe and Linda Dell in 1978, place cells basically act as X and Y coordinates in a Cartesian-style cognitive map of space, and encoding the relationships between spatial cues. And these are ultimately used to guide spatial behavior. And you can think of the grid cells as basically supplying the underlying graph paper for this map. Okay, so it all comes down to elementary school geometry. And as for this discovery of place cells and grid cells, that O'Keefe and Maybrit and Edward Moser shared the Nobel Prize for Medicine back in 2014. Now, in the media, the prize was typically described as a discovery of the GPS in the brain, which is a bit disappointing as it rather glossed over the idea of how spatial cells serve as a kind of Rosetta Stone for how the brain transforms complex sensory information into an internal representation of space. Now, to finally have access to this internal representation, is a fundamental idea that goes back in philosophy hundreds of years, at least back as far as John Locke. But another important point here is the close link that place cells have with memory, and how we've been able to use place cells to give us a better framework for understanding memory. So perhaps one of the most important phenomena associated with place cells is that of remapping. And this was a phenomenon first described by my PhD advisor, Bob Muller, and John Kuby, shown here, back in 1987. So as an example, we can see 12 simultaneously recorded cells. Some have clear place fields, while others barely fire at all. So when the rat is brought into a new environment, in this case from a familiar square enclosure to a novel circular enclosure, many of the cells from the first map turn off, previously silent cells turn on, and cells that are common to both environments have no clear spatial relationship to each other. So a simpler way of putting this is that the cell activity is completely scrambled between both environments. The hippocampus rapidly put together a new orthogonal, a completely separate map from of this new circular environment in about 5 minutes. It's remarkably fast. If we take the rat out and put him back in several minutes later, we see the fields are stable and will presumably go on to represent this new place forever, as the theory goes. So this business of making orthogonal or separate representations is thought to be exactly the kind of process that we need to form new separate memories. Now, while this point is still theoretical, remapping is still one of the best analogs we have for studying memory at a single cellular level, in animals at least, okay? So does what we see in the rat apply to primates? So anatomy of hippocampus and the entorhinal cortex are extraordinarily well conserved across rats, monkeys, and humans. And as we can see, this architecture of the hippocampal subfields, the dentate gyrus, CA3 and CA1 or CA4, is very similar, okay? So does the hippocampus also play a role in human spatial memory? So there was a landmark paper about 20 years ago by Ellen McGuire at University College London, and it suggests that it does. And she did the MRI studies with London taxi drivers, and these are people that make a living from navigating the complex spatial environment that is the City of London. So McGuire found that taxi drivers have a larger left hippocampus and right hippocampus than controls, which are people that don't make a living from doing a spatial job. But even cooler, she found when she looked at the taxi drivers, she found that the longer that they did the job, the bigger the posterior hippocampus got. However, this also seemed to occur at the expense of the anterior hippocampus, which got smaller. So, the overall volume of the hippocampus was conserved, just seemed to shift from one part to the other. But what about these spatially tuned cells that I mentioned? Do we see those in humans? And once again, this is a story where epilepsy research teaches us something very important about learning and memory. In the early 2000s, Itzhak Fried and Arne Ekstrom were implanting electrodes in human patients in order to find out where their seizures were starting so they could then have these regions of the brain surgically resected. And of course, here on the right, you can see that just like in the rat, these action potentials of excitatory cells look the same. So in this paper, they had the patients play computer games where they acted like taxi drivers. It would take these passengers to specific destinations in a virtual town, like the Griffin game store. And just like place cells in the rat, they found high firing rates of the cells in specific locations. Moreover, they found more spatially selective firing of these cells in the hippocampus and other brain regions like the perirhinal cortex, amygdala, or the frontal lobe. So I don't have the time to get into it. Other researchers have also found grid cells in the entorhinal cortex of humans, again emphasizing the conservation of structure and function between rats and humans. So lastly, just getting beyond space into more of what we typically think of as memory. Fried's group also recorded cells while showing patients pictures of scenes and celebrities. Then comparing the activity of entorhinal cortex hippocampal cells, they're responsive to these scenes while they're presented and while the patients were recalling these scenes. And importantly, these responsive cells tend to be active just prior to the patient's active recalling the scenes. Now, this already seems kind of dated, but we're going to see some video with an example of a hippocampal cell that's responsive to the scene of Tom Cruise jumping on Oprah's couch, as well as being active for the recall. First time you hear it popping. Here it is again. And again. Again. Last one. And in the next part, you hear the patient actively recalling the different scenes and pictures that they saw. And for almost dramatic effect here at the end. All right, so that is the end. I'm happy to take any questions that you might have. I'm not sure of the format, Dan. Is there questions now or a general get together afterwards for people to ask questions?
I think, yeah, there's definitely going to be questions now, and we kind of have it open until the next speaker for discussion and also for breaks.
Okay.
So I have a question for you, and it's kind of abstract. Can you hear me okay?
There seems to be a bit of background noise here.
Oh, hearing.
Can you hear me okay now?
Yeah.
Yeah. Better.
So I think of the hippocampus and kind of the example of space and grid cells as one example of thinking about neuronal substrates in us that create our perception and our reality of of spatial orientation. But do you think that applies to other things that we do and experience? Or do you think that the hippocampus is a very distinct system, and then other systems, other properties of what we experience are just completely different and recorded and produced by completely different neural substrates? Or how far do you think the hippocampus, medial entorhinal cortex as a whole translates to what is stuff that happens in us, if you will?
Yeah, and it's very similar. It seems like most brain regions kind of operate on a similar structure. And again, like this for one example, one idea is that excitation and inhibition is the same, and time.
Yeah.
And coincidentally, I had a great conversation a couple of times this week with Chris Moore. I presented at Brown last week, and he studies the sensory cortex. The idea, what is perceived? What does it take to get something consciously perceived? Which is very similar to how the hippocampus, might perceive something that would be a spatial stimulus that you can make spatial decisions on. So a lot of these operating principles of how cells are orchestrated by different oscillations, for example, that all lead into how do you make something be consciously perceived, and then use that consciously perceived stimulus to make decisions on. So long story short, the physiology seems to be kind of universal.
Yeah, that makes sense. And that, from my observations, when I was working in science, it was doing the work was very time consuming for me, and it was my main focus. But I was always thinking about these things, and I kind of wondered what other people think about it. Yeah, that makes a lot of sense, and it's good to know about these other systems. Also the perception and the decision making, those are all systems within themselves that are all overlapping too.
But yeah, again, like if you're going to take any point away from this, is that one of these universal operating principles, apart from excitation and inhibition, is that a cell should only be active when it's supposed to be active, right? And if it has a bit of information to send out down the line to the next cell, it needs to arrive there at the right time, which again is the basis of this theory that I've been working on, which is kind of a truism, right, of temporal coordination.
So what is the truism then? Or what?
It just has to be true. It just has to be true. Like, a cell might make an action potential that's not going to be made at the right time, and it just goes off a cliff and it doesn't make it to the next cell. But if it's part of a necessary processing element, that action potential needs to arrive downstream at the right time. Yeah.
All right. Thank you so much for sharing with us, Dr. Barry. I'm wondering if it's okay with you. We have had attendees to the meetings kind of asking if the slides will be available. If that's something that you are comfortable with, would you be willing to send us a link through an email? We'll reach out to you and then we can distribute it to attendees.
Absolutely.
Thank you. I appreciate that so much. All right, guys. So we're going to go ahead and we're going to take a 30-minute break. So, people, if you need to go and eat something or just decompress for a moment, that's totally fine. The room is going to stay open. We're just going to have a picture up that's just saying that we'll be back. And then we will be reconvening at 1 p.m. for our next speaker, who is Matt Schmier.
Okay, great. Thank you, everybody. And my email will be in the talk too, so feel free to email me if you have any other questions.
Thank you, Jeremy. Thank you very much.
A great time, man. Thank you for inviting me.